A register is a sequential circuit where binary data is stored and possibly shifted. It is a form of volatile memory and is frequently used in computer processors. A register is defined by how many bits it stores, which is equal to the number of flip-flops included in the register. Registers are synchronous circuits where all flip-flops share a common clock signal. There are multiple operations that a register can do. Hold, the outputs do not change when the clock ticks. Load, one or more outputs are updated when the clock ticks. And shift, each bit is cascaded through the flip-flops in one direction or another. The design of a register is defined by how the inputs and outputs are accessed. If all bits can be accessed at once, that is known as parallel communication. If the bits must be accessed one at a time in sequence, that is known as serial communication. The first type of shift register is known as serial in, serial out. This implies that both the input and output data is accessed serially, that is, one bit at a time. The architecture is relatively simple, as each flip-flop's output is connected to the next flip-flop's input. Typically, a serial in, serial out register can only shift in a single direction, from the first flip-flop in the sequence to the last. Serial communication usually requires some type of protocol to synchronize the input and output signals with a clock. If a clock is ticking, we want to be sure that the values written to the input flip-flop are accurate on each rising or falling edge. There are multiple serial communications protocols, such as SPI, USART, and even USB. Serial communication has an advantage of requiring fewer wires than parallel communication. For example, to write data in parallel to an 8-bit register would require 8 wires. But only a single wire is needed to write data in serial to an 8-bit register. The trade-off is that it requires more time to clock each bit through the register. In an 8-bit serial in, serial out register, it would require 8 clock cycles to shift an entire byte of data into the register. Then it requires 8 more clock cycles to shift that data byte back out of the register. In this demonstration, I'm shifting the data byte represented by the hexadecimal value 0x6A into the register. I use a push button to clock data into the register. Because the flip-flops were initially cleared out, the output, displayed on an LED, appears off for the 8 clock cycles where data is shifted in. The output data then appears one bit at a time on the next 8 clock cycles where I push the button to shift data back out again. Serial in, serial out registers are typically used as a kind of data buffer. Information is clocked in, where it can be temporarily stored until clocking it back out again. While we do not have a specific serial in, serial out register chip, you could easily build one using individual D flip-flops. The next type of shift register is known as serial in, parallel out. This means that while the input data is accessed serially, the output data is accessed in parallel. The architecture is still relatively simple, as each flip-flop's output is connected to the next flip-flop's input. But now, each output is accessible at once for communication to output devices or other circuitry. In an 8-bit serial in, parallel out register, it requires 8 clock cycles to shift an entire byte of data into the register. As each output bit is accessed at once in parallel, it doesn't require any additional clock cycles to shift the data back out again. In this demonstration, I'm shifting the data byte, represented by the hexadecimal value, 0x6A, into the register. I use a push button to clock data into the register. You can see each bit of data as it clocks through each flip-flop. After 8 clock cycles, all of the data has been shifted in and is accessible on the output pins. Serial in, parallel out registers are typically used when data that's received from a serial communication protocol needs to be accessed in parallel, say when saving serially received data into memory. We have an 8-bit serial in, parallel out chip the 74595. While we do not specifically use that chip in this class, it's not too difficult to figure out. If you take microcontrollers, we will use the 74595 to use a serial protocol to write data in serial to a 7-segment display. It's also relatively straightforward to build your own serial in, parallel out register using individual D flip-flops. The next type of shift register is known as parallel in, serial out. This means that all data bits can be written simultaneously in parallel, but the output must be clocked out 1 bit at a time, serially. The architecture is now slightly more complicated, as there must be a way to select between loading and shifting data. This means that each flip-flop input will be connected to logic that can distinguish between a load and a shift. If the load function is selected, information will parallel load into each flip-flop. If the shift function is selected, information will shift out of the register. In an 8-bit parallel in, serial out register, it requires 1 clock cycle to load an entire byte of data into the register, but 8 clock cycles to clock the data out again. I used the same data as the last example, in hexadecimal 0x6a. I select load by sending a low signal to the load shift pin, and press the clock button to load the data into the register. Then I select the shift function by sending a high signal to the load shift pin, and can clock that data byte out. I repeated this with the data byte represented by 0xA2. Parallel in, serial out registers are typically used when data that's accessed in parallel, for example, data stored in memory, needs to be transmitted using a serial communication protocol. We have an 8-bit parallel in, serial out chip, the 74165. That's the chip that I used in this demonstration. While we do not specifically use that chip in this class, it's not too difficult to figure out. If you take microcontrollers, we will use the 74165 to use a serial protocol to receive a byte of data from a dip switch and send it to a microcontroller using 1 data pin. Implementing this using individual D flip-flops would be slightly more complicated, as logic would need to be able to distinguish between the load and shift functions. We will do something similar to this in lab, and you can also figure out how the 74165 chip implements this by referring to the functional block diagram in the chip's datasheet. The last type of shift register is known as parallel in, parallel out. This means that all data bits can be written simultaneously in parallel, and the output can also be accessed in parallel. The architecture may be complicated if the register is capable of shifting data as well as loading and holding the data. If it can shift bidirectionally, then the input logic will be even more complicated. Because both the input and output values are accessed in parallel, a parallel in, parallel out register requires more I/O pins than other types of registers. For this reason, the parallel in, parallel out register chip that we have only stores 4 bits. A very simple 4-bit parallel in, parallel out register that can just load or hold data can be built by simply connecting inputs in parallel to D flip-flops, connecting the outputs in parallel, and connecting all clock inputs to a common clock source. In the demonstration on screen, I built this type of register with a quad D flip-flop chip, the 74175. Every time I press the clock button, whatever values are stored in the dip switch are clocked into the flip-flops and can be viewed on the LEDs. This process takes a single clock cycle to load and access the data. It's the fastest, but, as mentioned, requires the most wires. In this second demonstration, I used the 74194 chip, which is a 4-bit universal bidirectional shift register. This register is parallel in, parallel out, and has 4 functions: hold, load, shift left, and shift right. The input logic is relatively complicated, but can be deduced by referring to the logic diagram on the chip's datasheet. the function of the register that's being selected is configured via two mode select pins. In this demonstration, I start by loading the value 5 and then shifting it right. Then I load the value 11 and shift it left. I load the value 15 and then put the register into hold mode as I continue clocking the flip-flop. The register outputs do not change in hold mode. Finally, I load the value 10. You've already used the 74194 chip and will continue to use it in lab. It's one of the most versatile chips used for volatile memory in this class. I'm sure you'll be using it in portfolio circuits or design projects.